All right, today in Algebra 2, we're going to finish up Chapter 11. We're looking at Section 11.5, the margin of error. Our essential question, how can you determine how far a statistic is likely to be from a parameter? After today, you should be able to use margin of error to estimate a population parameter accurately. So number 1, it says Seth selects a random sample of students from a local college. He asks students their year in college and how far the college is from their home in miles. How can Seth's sample estimate the proportion of freshmen in the population? And then how accurate is the estimate likely to be? So we want to get the ratio of the freshmen. So ratio of freshmen. That's going to equal the number of freshmen in the sample divided by the number in the sample. So if we come up here and look at this chart and we count up how many freshmen are there, here's 1, 2, 3, 4. So there are 4 freshmen. So 4 out of how many total? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times 2, 20. So 4 out of 20, or 1 out of 5, which is 0.20. So there's our proportion, 1 out of 5, or 0.20. So that means 0.20 of the sample, or 20% of the sample are freshmen. The accuracy of this estimate is going to depend on the number of participants in the sample and how well the sample represents the population. Okay. If the sample clusters away from the mean, then it's not very accurate. Larger samples usually provide more accurate estimates. All right, it says use the sample data to estimate the mean distance from home. Then estimate the proportion of seniors to the total population of the college. So first, let's find the mean distance. And this is average, so we're going to add up all of the data. So like the 5 plus 50 plus 65, we're going to add up all of their miles. And when we do that, we get 2017. Divided by how many total are there? There are a total of 200. Not 200, there are a total of 20. We had 20 people in there. Sorry. So 2017 divided by 20 gives us 100.85. And then this was in miles. So there's our mean distance. Now we want the proportion of seniors to the total population. So let's find the ratio of seniors. We're going to find this the exact same way that we found the proportion of of freshmen in example number 1. So we're going to come back up here. We're going to count how many are seniors. So we've got 1, 2, 3 seniors. So out of 20. So that is 0.15 of the sample, or 15% are seniors. All right, example number 3. It says Tia is contributing to the same project as Seth and has sampled a different group of students. The proportion of freshmen in her sample is 0.4 or 40%. How can Seth and Tia determine whose result is a better representation of the population? We can have everyone in their class complete the survey. So everyone complete the survey. And then we're going to create a histogram of freshmen. The book tells us that there were 50 people that they did. Okay. So 50 people that they had take this survey. So the histogram, I'm going to go 0.1, 0.15, 0.2, 0.25, 0.3, 0.35, and 0.4. 2, 4, 6, 8, 10, 12, 14, 16. I'm just recreating the histogram that is shown in the book from the data from all 50 people. And so they have like up here, 0.1, they're down here at 1, they come up, about 6, and then go over, come up a little bit more, come up here to about 12, go over to about 2.5, down, come down. So this is a rough sketch of what the histogram in the book provides about the data that they gave. We can tell by looking at the histogram that this is a normal distribution. Therefore, it's reasonable to predict between 0.1 and 0.35 are freshmen. Because that's what this histogram tells us. Therefore, Seth's 0.2 estimate was good. Tia's 0.4 estimate is outside the range. Therefore, her estimate is more likely to be further away from the mean. So number 4 says, each classmate calculates the mean distance from home in miles reported by participants. Seth and Tia create a histogram to investigate the sample statistics. How many samples reported an average distance from home between 101 and 125 miles? Use the histogram to suggest a reasonable interval to estimate the population parameter. Okay, so again, here it tells us out of 50 samples, this is the histogram they created. Again, we can see it's a normal histogram. So we're looking at between 101 and 125. So between 101 and 125, that looks to be about 6 samples. So that took care of the first one. Then it says, suggest a reasonable interval to estimate the population parameter. So an average, a likely interval. between, so here and here. This is our good interval. So between 26 and 125 miles is the average likely interval from distances from home. So we're at our average, 1 standard deviation away, 2 standard deviations away. We don't want to go out here to the 3s. So that's how we're going to get that interval. All right, our next example. So our next example, Gabriella wants proof of Alex's claim that he is a 75% free throw shooter. She observes Alex shoot 50 free throws, of which he makes 30. Gabriella notes his 60% success rate, but Alex points out that this is a reasonable result due to the natural variability that happens from sample to sample. Is he correct? Is he truly a 75% free throw shooter, or is he not? So first, use random numbers. So here I just showed you, okay, you can do this in a spreadsheet, or our calculator will do random generation numbers. This is the chart that they made, and they said that they're going to use numbers 1 through 75 as successful free throws. And then they will use numbers 76 to 100 as missed shots. So with all of this data, the simulated probability was 0.78 or 78%. This is higher than her 60% that she got, but this is only one simulation. We would need more simulations for evidence of variability. So we're still not sure if Alex is telling Gabriella the truth. The top of the next page, I'm just showing you how your calculator, how you can get your calculator to be a random number generator. So if we go over to the math button and we go to probability, and then number 5, random, the INT stands for integers. And then tell it, okay, the smallest value you want, the largest value. So they did 1 and 25. And then if also in parentheses you put like 3, it'll tell you how many numbers you want to appear on the screen at once. Okay, so in Gabriella's, we would have done like 1, 100, since she wanted 1 to 100. And then again, if we'd put 3, it would give me the numbers in sets of 3. Okay, so we're going to continue the simulation, analyzing 100 samples of 50 shots each. The distribution of sample statistics, such as means or proportions from different samples of the sample population, is called the sampling distribution. How to interpret the sampling distribution. So this simulated sampling distribution is based on the assumption that Alex makes 75% of his free throws. So that this histogram and all of the simulation is based off of 75%, like he said. Let's look at where most of the samples are. So most of the samples are between if we come to here, like 31 out of 50 gets me 0.62%. And then over here, the 44 out of 50, which gives us 0.88%. So most of the samples are between those two numbers, my 31 It's really like Brecky. So most of the samples are between 0.62 and 0.88. That's where the majority of that lies. So this is as much as, okay, this is my average, 0.75 minus 0.62, so that's as much as 0.13 above or below the central value of 0.75. Therefore, 0.13 or 13% is a reasonable difference due to variability. So now let's check and see, does Alex match in there? Okay. So 75% free throw shooter is what Alex said he was. The accuracy with the variability would expect to be between 62% and 88%. Okay. Alex had 30 out of 50 shots. That does not fall within the 62 to 88%. Therefore, Alex does not make 75% of his free throws overall. Alex was bragging a little bit to Gabriella. All right, the sampling distributions of means and proportions tend to be normal. The mean of such a sampling distribution is the population parameter. The standard deviation decreases as the sampling size increases. According to our empirical rule, 95% of values in normal distribution fall within 2 standard deviations of the mean. So 95% of all sample results will fall within 2 standard deviations of the population parameter being evaluated. The margin of error gives the maximum expected difference between the sample result and the population parameter. We actually have a formula for this. So margin of error formulas. If we're looking at quantitative data or categorical data. So remember, quantitative, something that we can measure, numbers. Categorical falls into a category. The margin of error, and we'll call this capital E, is equal to 2 times the population standard deviation divided by the square root of the sample size. And this should actually say positive and negative out front of it. Positive and negatives. Categorical data, E is equal to plus or minus 1 over the square root of N, where N is the sample size. So let's look at some of these examples. So number 1, the College Board recently reported that the mean score on the SAT mathematics exam was 508 with a standard deviation of 121. Washington High believes that its seniors scored considerably higher than the national average. So the school randomly sampled scores from 200 seniors, finding a mean score of 550. Is Washington High correct in its belief? So first, let's find out what is the margin of error for this SAT. So our E is equal to, they gave us all the information we need to do quantitative data. So E is equal to plus or minus 2 times the standard deviation, which they told us, standard deviation of 121, divided by the square root of the sample size. The school sampled 200 seniors, 200. When we type all that in our calculator, we get that it's approximately plus or minus 17. Okay. The mean was 508. So if we do 508 minus 17 and 508 plus 17, this gets us the low. So 508 minus 17, 491. So scores as low as 491. 508 plus 17 gets us 525. And scores as high as 525. So that would be our national average between 491 and 525. Scores between there. All right. They said Washington Junior High. So Washington High, their average score was 550. That's much higher than this 525. Therefore, since their seniors scored much higher than the national average. So they are correct. Number 2, a random sample of 100 Washington High seniors reveals that 40% plan to take the SAT this year. Use the margin of error to predict the actual proportion of seniors planning to take the exam. So here we're going to use the categorical. So our E is equal to plus or minus 1 over the square root of the sample size. Their sample size is 100. So that's going to be plus or minus 10. So plus or minus 10%. Okay? They said 40% plan to take it. So 40 minus 10 and 40 plus 10. So 30% and 50%. So they should expect somewhere between 30% and 50% of their seniors take the SAT. Number 3, a polling company conducts a poll for a U.S. presidential election. How many people did the company survey if the margin of error is plus or minus 5%? It didn't give us any standard deviation, so this is going to be a categorical. So E equals plus or minus 1 divided by the square root of n. So in this one, we're looking for the n. We're looking for the sample size. So they told me that my margin of error, the E, was plus or minus 5%, which is plus or minus 0.05 equals 1 over the square root of n. We want to solve this to get n by itself. I need to get rid of the radical. It's a square root, so I'm going to square that. Square this. So plus or minus 0.05 quantity squared. The plus or minus goes away. 0.05 squared gives me 0.0025 equals 1 over n. This is a proportion, cross multiply, so I get 0.0025 n equals 1. I'm trying to solve for n, divide by 0.0025. And we find that n is equal to 400 people. When we were talking about all of our samples in our populations, we would look at, is this a good sample? Okay. They're conducting a poll for U.S. presidential elections. They surveyed 400 people. Okay. Everyone in the United States can vote, okay, right? Everyone 18 and over can vote for the president. 400 people is not a great sample, so that would not be a very reliable survey. All right, number 4. In a survey of 1,202 people, 11% said that they used the internet or email more than 10 hours a week. What is the margin of error for the survey? So E equals plus or minus 1 divided by their sample size, the square root of 1202. So we get plus or minus 0.029. So margin of error is positive or negative 2.9%. They just asked for the margin of error, so it's 2.9%, either above or below. Number 5, in a survey of 1,011 people, 52% said the television was their main source of news. What is the margin of error? So again, E equals plus or minus 1 divided by the square root of their sample size, 1,011. So I get plus or minus 0.0314. So approximately plus or minus 3.1% is the margin of error. The second part of that says find an interval that's likely to contain the exact percent of people who use television as their main source of news. They told me that 52% said that was their main source. So we want to add and subtract our 3.1% from their 52. So 52 minus 3.1, 52 plus 3.1. So when I subtract, I get 48.9. When I add, I get 55.1. So it is likely that the exact percent of people who get their main source of news from the TV will be between 48.9% and 55.1%. So that wraps up chapter 11 for us. This was 11.5 over margin of error.